And yeah, so in these next couple sessions, well, the next 3 sessions will be presentations from the science working groups, and then a lunch talk by Changpei Ma, and then additional presentations from the rest of the science working groups. So really the goal here is to arrive at the key science goals that are going to drive the architecture of this instrument. And then we're going to revisit those throughout the week and try to connect them with specific choices that we have to make on the design. So we'll hear from 4 of those science working groups in the next hour. And this is also our first scheduling change. So we're going to shuffle them around a bit. And the first one we're going to hear from is black holes in their cosmic context, which is a science working group led by Jose Gomez and Priya Natarajan. And Jose will be doing the presentation. So go ahead and share your screen whenever you're ready.
Thanks, Michael. Actually, the presentation is going to be shared between different, facilitators in our working group. So let me start. And Priya, would you like please to go through the first slides?
Yeah. Thank you very much. So I'm Priya Natarajan, and I have the privilege of co-chairing the science working group on science questions related to the demographic studies of black holes in their larger cosmological context with Jose Gomez. And we are delighted to be able to present the work that we've been doing for the last couple of months and share it with you.
Thank you very much, Priya. Okay, so we have here some slides just to show you the group members and also to describe that we had thought about it and how to distribute the different science stages in our working group. So, Priya, do you want to comment on the different focus teams or?
Yeah. Just coming there. Yeah.
Okay.
There are many fundamental open questions, and we have divided our science working group into 3 focus groups that actually tackle these very important questions. The 3 groups are black hole growth, led by the facilitator Angelo Riccardi, black hole binding,
I don't hear Priya anymore.
Yeah, no, I can't hear her as well.
Okay, let me see. Can you hear me now?
Yes.
Okay. I just wanted to close and turn it over to our facilitators by saying that we invite anyone who is interested in these topics, who is already not involved and would like to get in touch with us. So I turn it over now to Angelo.
Thanks, Priya. Today, I'll be talking to you about black hole growth. Here we're thinking about the coevolution of black holes and their galaxies on timescales of millions to billions of years, insights that we can get even by looking at relatively small snapshots in terms of cosmic time of what these resolvable black hole shadows can tell us. So we believe that black holes and their galaxies co-evolve. We find that black hole masses correlate with galaxy properties on scales much larger than their gravitational field of influence, with things like the total bulge of the host galaxy in terms of their mass and velocity dispersion, the latter of which is shown here in this plot from Cormody and Ho 2013. Black holes and their galaxies are linked by processes of fueling and feedback. Somehow the galaxy provides gas to fuel active galactic nuclei, or AGN. And when this happens, energy is released in the forms of jets, winds, and radiation, as shown here in the simulation on the bottom, where the merger of 2 galaxies drove gas to the centers, and then feedback from that accretion process heats up the gas and moves it away. We believe that AGN feedback is essential for regulating gas cooling in especially the most massive galaxies. And this is one of the most uncertain aspects of galaxy evolution models today. the evolution of these scaling relations with redshift are also highly uncertain, both observationally and theoretically. So any insight we can get from ngEHT will be useful here. Next slide, please. One thing that's particularly interesting is the evolution of black hole spins, even from what we can get at redshift of 0, because this encodes recent growth. Black hole spins are influenced by black hole mergers and accretion of gas. And both of these are very uncertain in the theory as well. In terms of black hole mergers, the delay between galaxy and black hole merger is quite uncertain, both on kiloparsec scales, where a messy cosmological environment can delay what one might expect from just analytic dynamical friction prescriptions, as well as how you solve the final parsec problem on smaller scales. And then when a merger occurs, the relative alignments between orbits and the two spins are uncertain. But a rule of thumb is that an equal mass merger will tend to produce a spin of 0.7 or so black hole, although this depends on the details of the orbit. For accretion, thin disk accretion can spin up a black hole, but the relative alignments between the disk and the black hole are uncertain. Spin can also decrease as jets are powered by the Blandford-Snijek process. And what I mean by this alignment is illustrated by these two models here, where we're looking at the evolution of mass of a single black hole at the center of a galaxy over a significant cosmic time. On the bottom, in this model, the alignment is always random. And so the black hole spin is really noisy and trending downwards because of this. Whereas on the right, prolonged prograde accretion disks over billions of years timescales will spin your black hole up to a maximum value of near 1. And black hole mergers can cause jumps shown by these circles. And it turns out that near the end of this black hole's assembly, the spin was dominated by recent black hole mergers, pushing it towards a value, like I said, that's roughly around 0.7. Even a handful of spin measurements from ngEHT would be useful, because these models are so uncertain. One can devise ones where all of the black holes are near 0 or near 1 or near 0.7, depending on one's assumptions. And if you're wondering at this point, hey, I know about these black hole spin measurements from X-ray reflection spectroscopy, for example, ngEHT would be interesting because the selection effects would be different. The measurements from X-ray reflection spectroscopy tend to give you high spins, but these are biased towards really efficiently accreting objects. And as you can see here, that can make a very big difference. So next slide, please. So our science case is trying to determine how supermassive black holes assemble over cosmic time, the relative roles of black hole mergers and gas accretion in the late universe. And more directly, we'd like to know how their masses and spins evolve with redshift. In terms of technical requirements, a sample of about 10 masses and spin constraints would constrain formation, fueling, and feedback from these black holes. And we expect roughly 10 horizon resolved sources to be accessible with millijansky sensitivity and 10 microarcsecond angular resolution, which would yield you a corresponding number of mass measurements and hopefully also spin constraints. But we think that further study is required to really determine the most efficient ways to constrain spin, both directly through photon rings, for example, as Shep mentioned before, which really directly probe the space-time, or perhaps indirectly from resolved polarimetry. In this figure on the bottom left here, we're showing the ether sample of potential ngEHT targets in terms of their ring diameters and 230 gigahertz fluxes, although the cyan points are actually, their y-axis values are currently not determined, giving you an idea of how our sample will be able to expand as we push forward with ngEHT. That's it for me.
All right, and I'll take over the binary pitch. So going from one black hole to two black holes. Thanks to the co-leads, Neil and Sarah, and the entire working group for the fantastic atmosphere. So you've seen in the previous slide that this simulation of a binary, of an accreting binary, and how spectacular these systems are to look at and to study from a theoretical point of view. And it would be nice to get our observational handle as well on these systems. The modeling can not only proceed with these complicated models, so we have to have a mixture of simplified models where we model the binary on a physical orbit, like a Kepler orbit or a post-Newtonian expression thereof, and keep the emission model very simple. So we're thinking about orbiting Gaussians, orbiting point sources, that sort of thing. I will emphasize that we will allow in the modeling the source to be messy and gastrophysical. So we can take a hybrid modeling approach, where we model what we know, in this case the binary orbit, and image the rest. This is a technique that we've been developing recently. And we can do all of this in total intensity and polarization. You can see how on the right, an image and how the measurements in the visibility domain can really help in identifying uniquely the motion of a binary, of orbital motion of the binary, and not the shadows itself. All of these classes of models are in principle already implemented in a fully Bayesian parameter estimation package called Themis, which thankfully is also already designed and capable to handle EHT and ngEHT applications of this type. Next slide, please. So speaking of the more physical, more complicated models, where we really run simulations, GR, MHD simulations, like we do for single black holes, they clearly run into additional challenges. These are much more difficult to obtain. But with my collaborators, we were able to identify a really computationally very efficient setup that brings now accreting binary spacetimes almost on the same computational footing as single black hole simulations. And one of the things that I'd like to bring to this working group is that we develop these models further. We're using a code that we are already utilizing for the Event Horizon Telescope collaboration. It has a number of benefits that it's already interfaced with radiative transfer codes, such as BOSS, who can handle the binary space-time as well. Next slide, please. And then we also talk about in the working group a lot about the source populations, and this ties, of course, very closely to what we heard before in the black hole growth section. There will be tremendous synergies with nanohertz gravitational wave sources that pulsar timing arrays and LISA are looking into. And these sources are very unique, especially if you compare to what LIGO is seeing. These will have an electromagnetic identification. These are persistent, long-term sources that allow a tremendous amount of physics that LIGO, for example, and other facilities simply cannot do. And I remind you of the ether sample that you've seen in another slide in another incarnation. And some of these sources might actually be binaries. And the more we're seeing, the more chances we have that some of them are binaries and can do tremendous things also for cosmology and black holes. The next slide was about how the science goals translate to the technical requirements, but there's a slide coming up where we summarize that anyways. So I'll stop here. Thank you.
I will talk about the multi-wavelength observations with the ngEHT. The ngEHT, along with multi-wavelength approach, will allow us to achieve significant progress in many case studies, such as disk jet connection, gamma rays and neutrinos events, nature of VLBI core, polarization and magnetic field properties, and also black holes properties and AGN radio loudness. To succeed, we need multi-epochs observations, multi-frequency observations, coordinated across the electromagnetic spectrum. This collage of M87 constructed by Juan Carlos Algaba shows very well both advantages and challenges of multi-wavelength observations. Next slide, please. Next slide, please. The ngEHT with the resolution finer than a light year will allow us to directly image the jet profile in the vicinity of the black hole, the location and length of the acceleration and collimation zones, and trace the jet down to the expected accretion disk and the region where the jet is ejected in at least in several AGN. Such images in combination with multi-wavelength observation will provide decisive information for theoretical models. And here you see the image of the M87 at 7 millimeters, which show a very rich structure of the jet and core region. And with ngEHT, we will get very good direct image between the black hole hopes and the jet. Next slide, please. The ngEHT will allow us to resolve and distinguish among the different regions where visible X-ray, gamma ray, and neutrino emission can occur. This requires time domain imaging to match events in the jet with outbursts of high energy photons or neutrinos, as we try to do at 7 millimeters with the VLBA Fermi Large Area Telescope, SWIFT, and many optical telescopes. You see here some plots at different wavelengths, and also VLBA images at 7 millimeters from BU Blazar programs, when we try to connect events in the jet with events at different frequencies. The neutrino AGN analysis will help us to understand how protons are accelerated to relativistic energy. That is an ultimate question on for the acceleration problem. Next slide, please. The ngEHT will resolve the VLBI core region with unprecedented resolution and determine its physical structure. The EHT has already imaged the core region of the Blazar 3C279, finding it to be dynamic with a puzzling multi-component structure. You see the images obtained by the EHT during the 2017 campaign. The ANHT will be able to map and track the polarized radio emission in the near vicinity of the supermassive black hole. Simultaneous multi-wavelength observation with the ngEHT can measure the Faraday rotation effect near the jet vertex to explore the medium both inside and surrounding the jet. This can determine whether the jet is confined by a wind and accretion flow or by its own magnetic field, and will allow to test the different jet formation model on scale of hundreds to thousands Schwarzschild radius. Thank you very much.
Thank you very much, and all the focus team facilitators. We are running quite late, so we are going to close just very quickly, just in the next slide that you will be able to also check online. We were just summarizing the different science cases from the focus teams on the three main science cases that we have identified in our working group. And we have also started to think about what are the technical requirements. And as you can see here, listed for each one of these main three science teams, there are some common requests, like, we need angular resolution of the order of 10 of microseconds or better. Of course, high sensitivity, the capability of performing multi-wavelength observations and monitoring. And we are trying to put all this together in our science traceability matrix for the working group. This is just an initial draft, and we will work on this in the next months. And we just have also submitted a document which summarizes the science cases of our working group to project scientist Michael Johnson and project director Chef Toleman. And this is all we have. So thank you very much, and let me thanks again to all the members of the working group for the very, very engaging activity in our working group. Talia, I'm not sure if you want to add any last comments.
No, thank you, Jose. You said everything. Yeah.
Thank you. Priya, any last word?
No, thanks. We just welcome anyone else who would like to join us. Thanks, Jose.
Thank you very much. We are happy to take any questions.
Yeah, so if you have questions, please raise your hand or put them in the chat. And then also for extended discussions, again, we encourage you to use Zoom. Yeah, and a huge thanks to all the members of this working group, and especially Jose and Priya. You're really setting the bar for the science across the project, and this is really extraordinary. I guess I had a question, which was the measurement of black hole mass and spin. That's clearly a really exciting prospect to expand that to many sources. I think we know how to do that for mass and have less of an idea of how to do that for spin. But I was curious for your science case, how accurately do you need to measure the spins for it to be effective? You want for these 10 sources, what accuracy do you need?
Actually, I think upper limits will be also very helpful. But I think Priya, you should be the one answering this question.
Yeah, no, I think as Jose rightly said, just upper limits, and in fact, just which portion of the spin distribution, whether they are skewed median spin, high spin, or low spin, even that will be sufficient, because part of the goal is to connect what we already know about active accreting supermassive black holes that are more distant, whose spins we know from X-ray measurements. This is a brand new view of nearby low accreting, non-accreting sources. So any constraints would be really welcome, and broad constraints on the spin would be sufficient.
Yeah, definitely some sources where we estimate spin in a few different ways would be quite exciting also, or mass. I don't see hands, let's go ahead and move on. But thank you again for the really nice presentations, everyone. So next up, we're going to hear from Christian Fromm, and we have two working groups, Jet Launching and Accretion, that have been actually co-convening their science working group calls. So Christian's going to give us an update on the state of both groups.
Okay, hello everybody. Can everybody see my screen?
Yep, it looks great, and we hear you fine.
But do you also see on the left the number of participants? Because
I only see your slide.
You only see my slides. Okay.
Yeah.
Good. So, as Michael just said, the Jet Launching and Accretion working group have been merged, and I would like to give you a short update on what we are currently doing in this working group. And I give this talk on behalf also of the other two coordinators, which is Matt Lister and Ramesh Narayan. And here's the outline of the talk. I will give you a brief structure of the working group, then the science questions we looked up, the next steps that we would like to perform, and a summary and an outlook. So the coordinators are, as I already said, Matt Lister, Ramesh Narayan. Lately, Jae-Young Kim joined us, and myself. So Jae-Young was extremely helpful. He created a homepage for us where we host our slides from the talks that were presented and also the recordings. And you can find this homepage down here. Typically, we meet every second week on Thursday at 13 UTC. And the meeting consists of 1 to 2 science talks and an extended discussions. The advantage of this group is that we have a really good mixture between theoretical astrophysicists, numerical astrophysicists, and observers. And we typically have around 40 participants. So this typically gives very lively discussions, also not only in terms of theory, but also how could we observe these things. And I really enjoy those discussions, and I hope we will continue with this kind of lively conversations during the meetings. And let's go to one of those science questions. With these questions you already have seen in the introductory slides by Shep. So one of these questions are jets powered by spin extractions? And how could we measure this? And one best bet is that we try to track substructure in the total intensity or the polarized images and find out what is their rotation rate? And we compare this with the rotation rate that we get from the horizon, which is written there as the equation, and check if the rotation is different in the disk or in the jet. So what do we need for this to establish this? So first, from the theoretical side, we need long-term duration GMHD. So up to 100,000 M or maybe even longer. And once we have those images, we would need to ray trace them and could create synthetic observations. And on those synthetic observations, we apply some feature tracking algorithms and see if we could see something that is rotating, and we could track it with high significance. One great database or work that was lately submitted and also presented in our working group was the work by Ramesh Narayan and collaborators. So what he did, he created several long-term GMHD runs for different spins. And you could see a result on the bottom left. So this panel is divided into two halves. On the left half, you could see the magnetization for a counter-rotating black hole with spin minus 0.7. And the gray line, which you see there, this traces the sigma equals 1 contour, and you could take this as a proxy for the width of the jet. And on the right half of this panel, you see the prograde spin. So spin is plus 0.7, and again, the gray line traces the sigma equals 1 contour. What you see is that the fast, also the positive rotating ones, seem to be a bit wider in the jet. Also, what we then do is we take those images, they are for 100,000 M, and we create GRRT images. And these GRRT images, we look for evolving and features that we can track. And then on the right side, you can see a picture that I took from a talk from Matt Lister. So Matt Lister showed us that with the Mojave survey, so the Mojave is the tracking of AGNs with VLBI experiments at 15 gigahertz. And as you can see on the x-axis, there is the time in years. So they do this now for almost 30 years. So they have a really, really huge database where they can track features in AGNs. And here you can see one of these innermost features in a radio map and how it oscillates around his average position angle. And the numbers here are, let's say it has an amplitude of 4 degrees, and you can see how nicely you can fit this. And the idea now is that when we could see this at 15 gigahertz, we can increase the frequency to 86 to 30 and check if we can also see those features in our synthetic observations and compare these rotations that we see in the synthetic observations with the one that we know from the different spins. All of those talks have been presented in the meeting. So the talks and the slides can be found on the webpage that I showed on the second page. Okay, then the second question is, that also Shep showed is, what are the physical conditions in the M87 or in general in the launching sites of jets? And one question there is, can we connect this rapid small-scale evolution with changes in other wavelengths? Also, in the previous talk, you saw that Svetlana Jostad showed this nice multi-frequency view of M87, which goes from the radio up to the TeV. And so what is going on there? Is this connected to some processes in the accretion disk? And last week, Bart Ripperda showed a very impressive talk on his latest results on super high resolution resistive GMHD. And I think he will also talk about this in this week's talk that he has, but also see the talk by Antonius Nathanael, which works on a similar field. And their result is shown on the left. So you have an accretion disk. This accretion disk is in a mad state. And what happens is you form this current sheet, which connects the disk to the black hole. This current sheet becomes unstable to tearing instabilities and form these plasmoids. So let's call them magnetic islands. And these magnetic islands are very efficient particle accelerator. And those happens on an oscillatory time scale. You could see that they have a certain time scale where these effects occur, and one could compare them maybe later via ray tracing and post-processing steps to this high energy observation that I show on the right from the Abramovich et al. Paper 2012, where you could see measurements from Hess, Magic, and Veritas. And this is also a way how to search for the signatures and compare them actually with observations in our simulations. Next one is, what are the boundary conditions? So in most of our simulations that we use for studying jets, we use an aligned system where the spin axis and the axis of the accretion disk are oriented in the same way. But there is no need that this must be the case. So also within our working group, Kaushik Chatterjee gave a talk on tilted disks. These are also large-scale simulations. They take several thousand amps, which they are evolved, and he tilts the disk with respect to the spin of the black hole. So at the bottom, you could see two of those images. So this shows the azimuthally averaged density, and one is for a tilt of 0, so they are aligned, spin of the black hole and the disk, and the other one, they are misaligned by 22 degrees. And you could find all of those images also in the paper that Kaushik submitted. And these images, when you take these simulations and ray trace them, they will give you a processing jet in those images. So again, if you're interested in the movies, go to the webpage of our group and look at the slides from Kaushik. He presented there a movie which shows you how the disk is processing. Again, these images can be ray traced, and this has been done by Kaushik and his collaborators, and you can compare them to observations. So he did this mainly for the case of M87, but one could take these simulations, run them a bit longer, and check for other sources. And again, when we look to the observational part, this was the talk by Matt Lister again, he showed that they have features which you can track in these jets images. So you can see this on the left side, you can see a quasar image at a certain time, May 2008, and there are two bright features. And these two bright features, their direction is marked with an arrow, and they are moving in different directions actually. But when you look for the long-term evolution, this is done on the right side. So when you stack all these observations that you have, they give you the large opening angle. So the idea here is, again, check if we could mimic such observations with our simulations. Okay, then one of those last questions, and I think, Michael, do I still have time?
Yeah, maybe a couple minutes. Is that
okay? Yeah,
yeah,
good. So then the other part, and this is also important, is which kind of physics do we need to include in our models so that they fit the observations better? Again, here, two very nice talks in our working group. One was by Yusuke Mizuno on heating models. So basically trying to get rid from these post-processing models where we assign our low and our high value on the electron temperature and let these temperature be evolved more physically within the simulations. So here you could see how different these images look. So maybe focus on the first and the second column. And these are the heating models. And they are from top to bottom, highly counter-rotating one, Schwarzschild, and highly positive spin, so 0.94. And in the third column, you could see how they look with these classical post-processing models that we used in the M87 papers. And you could see that you see a difference just by using a more advanced mechanism for getting the temperature of the electrons. Another part, which was interesting, was what happens when you include another species. So here, there was a talk by Richard Anantua and his collaborators. So in Imami et al., you can find these maps, and they show what is the effect, including positrons, in the polarized signatures. And you could see that when you ramp up the fraction of the positrons, that you get completely different polarized signatures. Again, this could be measured, and we can use this as a check for our models. And this is my last slide, and then I stop here. So the next step is that we now form small subgroups within our working group and try to work those models out. All these models, they can be of different complexity, so starting from one zone, semi-analyticals or simulations. These models don't need to include all the physics at the beginning, but we need some start and some standard set of tools that we can use and test our measurements and hypotheses. And of course, we also need to define, well, a set of statistical tools for the measurement and scoring of our models. And I leave you with this last slide that I took from Jose Luis Gomez talks, which lists you what we want to measure, what are the observation requirements, and what are the instrument requirements. Thank you.
Thank you so much, Christian, and also all to the co-coordinators of the group for this really nice summary. Any questions from the audience? I had one question, which is you mentioned this goal of understanding what physics is important on micro and mesoscales. And I was just curious, do you think this is something that we'll learn from ngEHT observations, or do you expect that it's something that we need to understand to make predictions for the ngEHT?
For example, when you look at these heating models that Yusuke Mizuno developed, and you create spectral index maps from them, and you create the spectral index maps from 230 and 345, or from 86 to 230, you will see that they have different distribution of spectral indices using different heating mechanisms. So I think that with the upcoming ngEHT images, when we will get them, we can test those things. And I think this is quite unique because you need not only high resolution in the disk region, so like what the EHT gave us, you also need it in the jet. You may remember this image that Shep showed at the beginning, where he showed the reconstructed image and the synthetic and the model. And if we get things in the resolution like this, this would be really helpful to figure out what kind of possible heating mechanism is going on in, for example, M87 or nearby sources.
Great, thanks. So I'd like to move on. There are some questions in the chat. Maybe you can answer them. Before we go to the next speaker, unfortunately Priya was muted inadvertently, so please be careful about that, about muting people when they're speaking, especially if it's multiple presenters during a single slot. So Priya is gonna give us the intro slides and also walk us through a bit of the STM in the black holes in their cosmic context group and at the end of this session. So we're tucking that in. So next up, though, Ziri Younsi is going to tell us about the key science goals and progress in the fundamental physics working group that he's co-leading with Vitor Cardoso. So Ziri, feel free to share your screen whenever you're ready.
Thanks very much, Michael. Okay.
And
Okay, so I hope that you can all see my screen and just my screen.
yeah, we see the slides. They look perfect and we hear you fine. Yeah.
Excellent. Let me just move some of these windows of other people. Just one moment. Okay. Okay, good afternoon, where I am in London, everybody. It's a genuine pleasure today to give this talk on the fundamental physics working group. But in particular, I give this on behalf of my fellow co-coordinator, Vitor Cardoso, and also on behalf of the many members of the fundamental physics science working group. It's actually quite a large group. We have a regular attendance of over 50 members. And so, as you can imagine, given its fundamental physics, we're quite a broad church. And to get things started, excuse me. So we actually began our working group, excuse me, I apologize for the There we go. So we actually had our first kickoff meeting in the middle of September on the 16th. So we're probably the youngest group in the collaboration, but I would say that we probably cover the broadest range of science topics. Being tasked with working on fundamental physics is ambitious, but there are many, many wonderful scientific returns that are possible. And in particular with this new next generation EHT instrument, we have the capability and potential to do something more than just having a simple measurement of an image. We can really start to drill in deeper into the fundamental physics, the space-time geometry, and so on of next generation EHT black hole measurements. And so we had a little bit of organizational structure. So what I'm going to show today, given we've only had the first few meetings, is what we've done in terms of structuring the group. So identifying science priorities and soliciting input from the group. So we actually constructed a survey. And this was important because we had over 130 people signed up. And so as you can imagine, we wanted to have a sense of people's interests because we are quite a broad church. And in so doing, I apologize, my slides are not changing. Sorry. Apologies for that. We submitted a survey. We had over 60 responses, which was excellent. This really gave us a chance to see what is going on in terms of people's interests. And we started as a reference point with the 5 main science topics that were identified in the ngEHT Winter Science meeting at the beginning of this year. And so they're listed here from A to E on the left. And we asked respondents to rank these topics from most important through to least important. And you can see the results broadly on the right, broken down per topic. But to give you just a brief overview, this shows the first 2 primary considerations. So this is the sum of those topics which people considered either most important 1 or nearly most important 2. And you can see that there is a clear favor towards measuring spin of the black hole or space-time tomography. We also saw that a lot of people are very interested in photon ring detection. Interestingly, not that many people are interested in this working group in measuring black hole mass. But of course, black hole mass is a fundamental component of the multipolar structure of a black hole, so it's something we will encompass. But we wanted to get a sense of what people are interested in so that we can define topics within the working group that are not just structured around core ngEHT science goals, which is of course of primary importance, but also very importantly around the group's interests. So, excuse me, having technical issues with my slides today. I apologize for that. And so, after we had a look at these results, we did actually ask one more question, which turned out to be incredibly interesting, which was, if you had the option to suggest one more topic that isn't in this list, what would you suggest? And there are a lot of responses again, some multiple responses. And the most common suggestions were actually, first and foremost, tests of the Kerr paradigm, and beyond that, of the underlying theory of gravity itself. The connection to gravitational waves in cosmology, and people also very interested in jet physics. So for example, can we study Blanford's Nyack mechanism? Can we understand how the jet base couples to the black hole? Is it coupled through the magnetosphere, the ergo region, and so on and so forth? And people are interested in accretion of non-Kerr spacetimes too. So these were what we consider perhaps to be 3 quite core topics that many people suggested. But beyond those, there were suggestions to look beyond n=1 photon rings. People are interested in horizonless compact objects. So for example, black hole mimickers, people mentioned boson stars, gravastars. Some people mentioned naked singularities. And a lot of people mentioned flaring and time variability. And we had several discussions on this. So the final feedback that we got from our group thus far is to do with the time zone. We're actually very broadly distributed. So we have quite a large contingent in East Asia. as well as, of course, many people in North America and distributed roughly around Europe. And so this has actually allowed us to converge on quite a narrow band in time to have our meetings. So we have fortnightly meetings, and we alternate between a Wednesday and a Thursday. And this is just to allow for people's schedules. So we actually had a follow-up survey to determine this. And yeah, that it's roughly at around 2 p.m. UTC every fortnight, every 2 weeks. And those of you who are interested, you are very welcome to join. Just send Vitor or myself an email and we'll add you to the list. So I do apologize for my technical issues, everybody. Continuing on. So after this first meeting, we've since had 2 more meetings. So last month we had 2 meetings. The first, we decided we want to engage more with the working group and get people discussing, because we've got a lot to cover, right? And so we had discussions and presentations from 10 group members who were chosen somewhat randomly, but in such a way that we knew that their interests cover a broad range of the different science priorities within our working group. And actually this was excellent. People gave wonderful talks, and thank you again to everybody who's spoken thus far. And more of you will be invited to present soon. And we had several important discussions on these topics that I mentioned in the previous slide, as we've been working towards the science prioritization, and also to get people's feedback on these suggested additional topics and the means by which we can investigate these. And in our most recent meeting, we've continued this theme, and we've heard from more group members. And as I say, this has really been wonderful to hear what people are doing. And what we've done actually in this last meeting has been able to shape our remaining science priorities in such a way that we have identified 8 broad topics. And within these 8 topics, there are some new themes that we are drilling in on now. And so here are our topics. So of course, the first is to measure the black hole mass, and there are many means through which to do this. And perhaps the principal one within our working group would be to measure the diameter of the black hole shadow itself. Measuring spin, this is incredibly fundamental and important. Photon ring detection is a third topic. Okay, skipped ahead. Fundamental fields, so that could be measuring axion fields. It could be even measuring heavier fields like dark matter. There's quantifying horizon physics, of course, tests of Kerr paradigm and GR. And interestingly, the connection with accretion and jet physics wasn't mentioned in the winter meeting as a topic in its own right, but there was such a push for this and so many people in the working group interested that we decided to do this. And of course, one of the directions that we can play with here is GeoMHD simulations and probing the time domain of variability from accretion flows around perhaps non-Kerr black holes or even horizonless compact object systems. And there have been studies recently on this. And finally, there was also a lot of interest in making the connection with gravitational waves, and in particular binary black holes, especially binary supermassive black holes. And several members are actively working on this and gave some very, very insightful and valuable talks on this. And dynamical spacetimes, of course, are a wonderful way to get into that dynamical regime of general relativity. And we've seen, actually, we've heard in the previous session from Roma and Gold, who's working on these things too, that there is a lot of synergy there with different working groups and with gravitational wave observations. And that's something that we seek to pursue as well. And actually, after hearing from the various people that have very kindly presented thus far, we're actually in the process of establishing the science leads for this. And in the next fortnight, we should have finished this. And so we'll be ready to move forward on these topics. However, within these topics, we decided we need to rank them and focus our key priorities in this working group moving forwards. And this is something that, of course, we'll have the opportunity to discuss today and throughout the meeting this week. So black hole mass and black hole spin. Within the context of the multipolar structure of space-time, they are actually interrelated, also with the quadrupole moment and so on. So these can be grouped together in terms of a key science goal. Fundamental fields in and of themselves are a fundamental physics goal, and they stand in their own right. And finally, we've identified tests of the Kerr paradigm and of general relativity itself as another separate topic. Other aspects of this, so for example, photon ring detection, can be thought of as a tool, as a facilitator through which we can do things like constraining spin or constraining mass, or polarization measurements, or a fundamental means through which we can probe and constrain fundamental fields, right? So they're a sort of facilitator rather than a sort of prime, they're a driver. And the same can be said with gravitational waves and binary black holes. They're sources which enable us to drill in and constrain these sorts of things. So So finally, after much affair with my laptop, we've identified the following 3 key science goals. So the first is controlling the black hole multipolar structure. This is key because we want to understand not just the Kerr paradigm, but also going beyond general relativity itself. And through this, of course, we want to facilitate tests of Kerr and of GR. And finally, fundamental fields, how they couple, how we can constrain these are very important things that the ngEHT can enable us to do, which the present EHT cannot. And as I've mentioned, there are some primary science drivers. These are the main 3. And everything else, in a sense, can be seen as serving as a tool to enable these goals. And we hope there will actually be a Lego exercise this week that we can discuss more about this and try to define some instrument requirements. So, for example, what would it take in terms of, as an example, an angular resolution to resolve a particular aspect of the photon ring substructure to get a good constraint on spin, or when looking at what would be a reliable candidate binary black hole source. A lot of people have said OJ287, are there any others? And then how does the mass ratio impact things, and so on. So there are still a lot of open questions, and we're actually working very hard within the group and within the subgroups that we're defining now to identify the key drivers here. But what I want to say is that we very much value your input here, and both myself and Vitor welcome any questions, any discussion you have, either now through the chat or just send us an email, and we'll be here all of this week. And we very much look forward to hearing from you all. So with that, I'll stop there, and apologies for the interruptions there. Thank you.
No worries at all. Thank you so much, Ziri. I will take one quick question, and then we're going to circle back to the black holes and their cosmic context, and they're going to discuss a model for science traceability. So Andre, the question is yours. Yeah.
Hi, Ziri. Very nice presentation. I presume you get the number 2. Is some by default or by implication the test of distinguishing between black holes and their alternatives? Is that correct, or is it now falling off the list somehow?
So good question. So of course there's multiple pathways through which to do this. So one could be, so if you have an alternative perhaps to the black hole, so perhaps some horizonless compact object, you could have a better dynamic range, for example, in the ngEHT. You could resolve this central brightness depression, and you could say, okay, with M87 we saw roughly an order of magnitude, but that is of course the dynamic range of the current EHT. What if we have 1,000 as a dynamic range? And then we find out that the flux ratio between the edge of the shadow and that central brightness depression is only 20. Does that enable us to put some constraint on the properties of that central object? But there are of course other ways to do this. So you could like perturb space-time away from Kerr. You can look at parametric metrics. So there are many such metrics in spherical symmetry and axisymmetry. And we could do things as simple as just looking at photon rings, or we could do things as complex as full GRMHD simulations. And so there's a lot that we can do. We have a lot of scope. And so the question is, what's feasible in the short to medium term and with the resources we have available in this group?
I think as a goal definition for ngEHT, you may probably want to be sort of broader than just saying tests of Kerr metrics. Okay.
Yeah, so I think that is a good segue on to onto this discussion of science traceability. So I'd like to move on to that since we want to stick to time. But thank you, Ziri and Vitor, and also I'll note that there are some nice comments and questions in the chat. So I guess Priya, are you all set?
Yeah, thanks very much, Michael, for giving me this chance again, because I didn't get because of audio issues, I didn't get a chance to showcase the vibrancy of our science working group. And I just wanted to mention that we have 52 very active, enthusiastic scientists across career stages who have participated in what we presented and showed you. And this is partly because of the many open fundamental questions, right, that are pertinent to the formation, fueling, and feedback from supermassive black holes. And I wanted to just zero in a little bit on a very preliminary science traceability matrix work, just to show you and how we have been thinking about developing this. And I wanted to zoom in on sort of one of the questions that we have looked at, which is, for example, we started with a meta science question just to give a sense of the structure that we have followed. It's just one template, and we are willing to learn to hone this better. But we started out with the fundamental science question of how do actually a supermassive black holes form.
We lost your audio.
The role of accretion versus mergers. Can you hear me now?
I do hear you. Yeah, it dropped out for a moment. Sorry.
Okay. So we've kind of circled through with that big science question, looking at objectives, then looking at the measurement requirements and the observational requirements, and therefore then ratcheting on to the instrumental requirements. So just wanted, this is by no means complete, but this is just an example of the flow that we have come up with in our group. So Michael, that's all I really wanted to say. And I think that, we have organized our questions, our science questions, on the basis of how we can build upon uniquely with ngEHT, given that we have a lot of information from other wavelengths for accreting, more distant accreting black holes, masses and spins and so on. So what can ngEHT uniquely do? So that has been what has driven our sort of motivation for phrasing it this way. Thank you very much.
Thank you so much. And just to kind of go back to the morning sessions, our plan is that we're going to identify 6 science goals that we're going to really zoom in on during this this architecture exercise that the systems engineering team is leading later this week. So if you, I think we're really going to try to learn from this structure that Priya just presented and try to match that in some of the other working groups where maybe we haven't connected to the sharply defined instrument requirements. Okay, but we have just a couple minutes, so I'll open the floor to questions either for Priya or for any of the previous speakers. I also want to acknowledge it can be really daunting to unmute and to ask questions, but this is meant to be an informal place. So don't be shy about turning on your video or reaching out. Maybe I'll just point out one thing. So Ava, you had posted a comment in the chat. Do you want to say something about that? I think.
Oh, hi, sorry. Exercise bike, so this is not an image anyone wants to see, but here it is. No, I'm just wondering what the status is of super high energy collisions near the horizon. This is something that goes back a long ways in particle theory. When we take into account the extension of the objects that occur in gauge theories and also in string theory, the range of that interaction gets larger. It depends on having a high spin, but the range of interaction being large means it's not necessarily as tuned as it was once thought. Anyway, my question is that figuring in, or is that just way out of reach? This is kind of Fanny knows Silk West, but update to that is my question.
So Ziri or Vitor, did you want to comment on that?
Vitor, would you like to jump in, or shall I field this? Okay, I'll jump in. Thanks for your question, Ava. Yeah, so I guess I followed it up briefly in the chat. You're referring to particles, right? So we're talking about atomic physics here. I would say that unless...
Sorry, I lost context, so I didn't see what you said in the chat.
No, sure. So you're referring to atomic physics?
Like string-like objects, so gauge flux tubes, or actually even fundamental strings was the question.
Right. I mean, my off the bat answer would be, it's not something that we could detect with an interferometric experiment like the ngEHT without there being some kind of signature. It could be some kind of electromagnetic signature. It could be some kind of physical process which mediates something that we can detect. If there is something which connects this microscopic, or even in the case of strings, right, you know, this is a Planckian scale type thing that connects to something of the macroscopic scale that we can measure, then we're in business. But my gut response would say, I'm not sure that's something that we can presently do with radio VLBI.
Yeah. The point is that the curvature scale does not dictate the scale of the interaction, so it's not as ridiculous as it first sounds.
No, it's not ridiculous, and I agree with supermassive black holes. The local curvature is very weak, so that's absolutely the case. I agree. It's just more a question of, you know, what would be. There's so many other competing processes going on there, right? The closer you get to the event horizon, the more you see high energy energetic phenomena, and you know, is what you're referring to something which is a sort of, you know, it's like not even a needle in a haystack. It's just such a minuscule effect that it would be it'd be very hard to pick out of all of that other continuum, so to speak.
That makes perfect sense. Just checking.
Is it worthwhile thinking about a limit one could set based on this? I mean, you know, it's likely to be a very small effect, but could you ask?
Yeah, I mean, I think the question is what was said, which is like, you know, disentangle it from everything else. That's always hard, right? But maybe it has some feature that is distinct from astrophysics. But I have no specific proposal. It's just tempting because of the.
No, these are absolutely the sort of questions which I think need to be asked, right? And more than that, if it is something which in principle we can quantify, then we can, again, in principle, constrain this. Even if it's a ridiculous constraint, it's a constraint nonetheless. And I think in this fundamental physics working group in particular, we keep a very open mind. And you know, if you'd like to discuss this more, like, please do just send myself or Vitor an email, and you know, it'd be great to talk with you more about this and, you know, really get into the detail of it, because I'm sure you have something very particular in mind.
Okay, with that, I do want to make sure that we have time for a short break before the next talk by Changpei Ma. So that's going to happen at the hour. And also, you know, these are conversations that are really expected to continue throughout the week. So please continue to think about these ideas and bring your questions as we're connecting this with architecture. Okay, so see you all in just over 10 minutes.